Great. Thanks, guys. So, I, just as a little intro, I actually had my first time with this group at the last session when we talked about test. And I came up to Mickey and I said, hey, let's do more talks on cool stuff. So, we're going to talk about concurrency today, but I want to make an open invitation that if anyone has fun topics to talk about in Golang, this is a sharing community. So, please come up after, talk, bring your ideas, add to the community. It only grows as much as the community wants to help. So, cool. What I want to introduce first is on the top, we have a link for where anyone can submit questions. You could submit questions personally or anonymously. I'll have the question form open up when we go for a break, but if you want, you can write down the URL now if you have, but I'll also put it up later as well during the break. And we'll have a session after the talk for during the Q&A. We'll answer any of those questions that have come up. So cool. So without further ado, let's get started. So just some quick information about who I am. So I moved to Sweden about a year ago, and I moved here from New York. A lot of people ask me, why did you move here from New York? And I said, I moved for love. I don't have my ring on today because I had a rash, but I am married. Trust me, believe me, it's not a lie. The marks are there. But I'm just recently got married in June to a lovely Swede, and it's been cakes and rainbows since. Super lovely. But since I moved here, I'm working as a full stack developer with Apsis. If you don't know Apsis, we do email marketing for IKEA, H&M, and a ton of other companies as well. I did my master's in software security at a school called Iona College right outside of New York. I also did my bachelor's in computer science. I've done research. I've been published on IEEE about 4 times for my research in various things. Just come ask me about it. No need to brag extra on that. And I've been working as a full stack developer for about 7 years and super active as an open source contributor. Lots of fun projects that I've helped out with, including SAS, if anyone knows. Yeah, everyone knows SAS. SAS is fun. Just don't get sassy. So, I would say sit down, but you guys are already sitting down. But we need to talk about something hard to discuss. I want to get some things straight before we start having this talk. So we're going to talk about some tough stuff. The first one, Santa's not real. Flat out, get that out there. Santa's not real. I'm not bullshitting. But no, let's skip past the jokes. What I really mean here is that concurrency is not parallelism. So this is the focus of today's talk. I want to clearly explain this in the beginning, and then we'll start talking about concurrency and what does that mean for the language of Golang. And we'll talk about, how can you use concurrency? I like to coin off of a nice thing from the previous talk that we had in the community about how you don't need third-party frameworks when you use Golang. Everything's nice and baked in. So we're going to talk about only native concurrency that comes with the language. And all the examples are runnable code. I did test everything out before. So what is concurrency? Well, if I wanted to tell you about concurrency, I could pull up an article from Wikipedia and explain all the nice things about concurrency. But this is not what we're here to talk about. We're here to have fun. We're here to get engaged. We're here to have exciting talks about concurrency, not read through some boring material. So what is concurrency? Well, if anyone has watched the talks online, specifically from Rob Pike, who was the inventor of Golang from Google, you would read that it's the composition of independently executing processes. I speak at a 5th grade level, so let's not use that. But what we mean is we don't mean processes in the sense of command line instances. We need to think a little more abstractly. So what that means here is that we are talking about like a car here. So when we have a car, we have a lot of things running on the car as you're driving through town. You have your engine running, you have your front tires spinning. If you're going in reverse, you got your back tires spinning, and you got your brake lights. So when we're talking about concurrency here, we're meaning that your program, your application that you write is this car. There are many things going on in the car or your application at the same time. And I'm not saying in the sense of like I call one function and then I call another function. I mean like you call two functions and they are doing things separately at the same time. So the next thing is, what's parallelism? So parallelism is the simultaneous execution of multiple things. So what we mean here is take the example from before and times it by 3. That's parallelism. Concurrency, you got your brake lights and your engine running at the same time. Now I'm messing myself up. But concurrency, you have your car running with the engine running and the brake lights going. Parallelism, you get another car and you're running both cars at the same time. If that makes sense, then we'll move forward. Nice thing to know about the thing before is that sometimes those cars don't have to be running in, let's say it's applications here. Those applications don't have to necessarily run on the same computer. They could run on different computers. If you're running in the cloud, you could have multiple servers running your code. That would still be considered parallelism. They don't have to be on the same machine. So now comes the big and obvious question. Why do I need concurrency? And I hope everyone has a reason here for why they're at this talk to talk about concurrency. And I want to answer that right away. Let's get to the real nugget here. So why do you need concurrency? You don't. That's the short answer. I really want to stress this out as an extremely important aspect, that for concurrency, you should never directly dive into concurrency. It's not something that you should jump to as an answer for your problem before you even solve your problem. So really, really want to stress this. You really don't need concurrency. But in case you do, what does this mean for Golang? So it's a commonly misunderstood problem that concurrency is something that every application needs, especially when you start working with Golang. When we get into the next set of slides, you'll start to see how simple or how basic it might be to start using concurrency. But what ends up happening to a lot of people when they start using concurrency or thinking that they use concurrency is that they take their program, for example, and they run it into 4 separate processes. And they think, well, if I run my application 4 times over in 4 separate terminal windows, it's going to run faster. And then the reality kicks in, it actually doesn't run faster. But what went wrong was that it wasn't necessarily their application that failed to run faster. It was their understanding of concurrency. So at the end of this talk today, I hope everyone will have picked up something and understood the difference between concurrency and parallelism and how to use concurrency. So let's talk with a quick intro about concurrency and what that kind of means. So when we say Golang is concurrent, you might work with other languages like Java and C#. These languages require additional libraries. I know with C# you need to include something called Microsoft TPL Dataflow if you want to use concurrency or use system threading. But what I want to say here is that Golang has concurrency built into the language without an additional library. And this helps with making the implementation of turning anything in Golang into a concurrent execution super easy. And all you have to do is say go. So as we go through the rest of the talk, because we have to have go jokes, we'll be using this go keyword quite often. So let's have a short introduction into Golang concurrency. So channels are a way to exchange information between Go routines. If you kind of think about it, channels in Golang work a lot like queues, but they're different, and we'll explain why. You can use them as buffers, and the nice thing that I like a lot, and I didn't know about this right away until someone actually told me, was that when you use a channel, channels are thread safe. So if you have a lot of things listening to one channel to pull items off this queue, it's thread safe. You don't have to do any thread checking or worry about deadlocks and stuff like that. And if you are using a buffered channel, which we'll show here, you can loop over a buffered channel infinitely until it closes. It is not necessarily a blocking command, but you can loop over infinitely with a for loop. The other thing about Golang concurrency, which will be kind of your crutch, your staple for the language, is the select keyword. And the select keyword is a decision-based keyword. So it helps you implement switch-like functionality throughout your code, where you want to say that I want to listen to multiple channels for information, and the select keyword will help you with picking from multiple channels for inputs. It's extremely helpful when you want to avoid creating blocking code, where you want to listen to one channel and then only, go to the next one as well in case there might be an input from the other one. But the key thing is that the select keyword is executable one time. So if we look at the code on the right here, we have a job structure with our main function, and we create a queue. And this specifically here is an example of a buffered queue. If I took the number out over here, I would have an unbuffered channel. With an unbuffered channel, it's more blocking in the sense that as someone is pushing an item into the queue, that person pushing the item has to wait until someone can receive it before continuing. The difference here is that if you use a buffered channel, you don't have to wait. You can continue going and do other stuff. So in this example here, I create a buffered channel in which I push on a new job to say hello world. And we have a loop here. And we also have a question. So when the 10 items are up, it continues to live. The queue will keep going. That's actually a really good question. So let's say I create a buffered channel. Just to repeat the question, so if I have a queue and I push 10 items onto a buffered channel with a size of 10, what happens if I push one more item, for example? What happens there is that then becomes a blocking call. Yeah. And you have to wait until space is available on the buffered channel. So yeah. But continuing with the example here, I push on one item into a buffered channel with a space of 10, and then I create an infinite loop pulling items from the channel. On the first call, I'll get this job that I had just put on, and I'll print out the information, and then I'll infinitely loop every second, checking to see if other items are pushed onto that channel. So does this make sense here for the most part? This is really kind of a really easy introduction, I would say, to Golang concurrency, and then we'll start talking about patterns next. So let's start talking about common patterns. So what I wanted to do here is I wanted to take out some really common use cases for really common use cases that someone might come across for using concurrency in Golang. We'll give some examples after we talk about the pattern, but to start, we're going to talk about fan out, fan in, and greedy consumption as concurrency patterns. So the first one, fan out. What we talk about here is the idea that in a concurrency model, you will have one producer with many consumers. If anyone has used AWS before, this is a very similar situation to Kinesis. When you use Kinesis, you push items onto the service, and then you can have one or many people reading from this streaming service. In this case, this is a more local implementation of how you may use a channel to hold items and have multiple Go routines pulling items off the channel to work on them. So with the example on the right, we have the job that we had from before with a little more information. And we have a job queue, which is a buffered channel of size 1. And then we create a worker. Worker is kind of like a common pattern for just basically saying someone who pulls an item off of a channel or off of a queue and holds that item and does some kind of work with the item before continuing on to another item off the queue. So for this one, this is the point that I said earlier about how with channels you can range over a channel infinitely. Now, if you range over a channel, you might think, well, okay, I'm creating a for loop. It might work like an array where I go from 0 to the end and I go back. When you range over a channel, it doesn't go back. It only goes forward. More importantly, if I had a buffered channel here with 5 items and I had no items in it, and I ranged over the channel, I would sit and I would wait until an item is available. And as we said earlier, channels are thread safe. So as I'm waiting for one item to come up, and I've basically the first one online, waiting, I'll get the first item, and then anyone else who's waiting has to wait till the next item. I don't want to overcomplicate this too much, but just in a sense that if you use this for all of your workers, you'll implement what's known as a round robin style for picking items off a channel. It's a nice thing to know when you get into the nitty-gritty of Golang concurrency. So beyond the worker, we have our application. And in our application, we have a done, which is more of a channel with a Boolean that holds one Boolean item. We create 5 workers. And for here, we loop about 25 times. And each time we're printing or creating an item, a job, that will get pushed onto the queue. So we push 25 items to the queue. Important here is that this job queue only holds one item at a time. So as this loop continues, as to the previous question about what happens when you push onto a queue that's full, or a channel that's full, this will be a blocking call. So this will block infinitely, pushing one item at a time into the job queue. And each time it's pushing an item, the workers will pick up in a round-robin fashion to take items off the queue. And then lastly here, we have a Go routine that is generated. So this is something called a anonymous function, if anyone has not seen one of these before. But in this anonymous function, we're going to sleep for about 2 seconds, and then we're going to close the queue. 2 seconds is more than enough time for this to push all the items onto the job queue. And then when this is executed, we're going to say that we're officially done pushing all the items onto the job queue, and all the workers will be finished doing their work. So in this fan out pattern, we satisfy it by having one queue that holds items, which is our producer. And then we have many workers listening to that one queue to pull items off. So do we have any questions on this? No? Cool. So we'll continue to the next. Yeah. Sorry, my apologies.
The anonymous function at point.
Yes.
Is that like started at the same time as the same worker, or is it
Yeah. It's a good point. So for this here, this is blocking because this is a for loop, and a for loop is blocking. So the next statements won't execute until this is done. But this is a blocking statement. So this is going to try to push all 25 items onto the job queue before going to the next step. But once it gets to this step here, this will run instantly and then quickly jump to the next spot. And I'm glad you brought that up because this is a good point here. In case you ever wanted to create blocking code, this is an empty, just pull something off the channel once something is pushed onto it, but wait until something exists in the channel and then pull it off. So by putting this here, this will block until this line is ran. And if you ever have to write code that needs to kind of wait infinitely for items to be processed off of a channel, this is one way to do it, and we'll have many different ways throughout this talk on how you can do this, keep my main function alive until everything is done. So yeah. Cool. So like I said earlier, this fan out pattern can be used and is used quite often as a architectural pattern for things like AWS Kinesis, Kafka. If anyone's used AWS SNS, which is a message broker, all message brokers basically implement the fan out pattern, and RabbitMQ. So it's a very common pattern that's used as almost an introductory to concurrency. So the next thing I want to talk about here is the fan in pattern. I do apologize, the code on the right is a lot smaller than I had expected. But the way the fan in pattern is basically do the inverse. So now you have multiple producers pushing into a single channel, and you have one consumer on the other end. And the way you might use this pattern is when you want to be able to react to multiple inputs. If you don't necessarily know, or you do know that you have multiple sources of data that are coming into your application. A good example for this is that maybe you are, let's see, I'm using AWS because at my current job we do a lot of AWS work and cloud work. So if in the cloud you have multiple databases and you're reading in database records from your database using a streaming system, then you may want to create a consumer who reads from those streams, multiple streams of data. This is that pattern. So for this kind of pattern, you'd want to use the select keyword to read from multiple channels. And the way the select keyword is interacted, and I want to go earlier so that we can actually see a little clearer. But when you use the select pattern here, which looks a lot like a switch case, for every case that you provide, if anyone has used switches before in their programming, usually when you use a switch statement, it goes one by one, depending on your programming language of choice. But in Golang, when you use a select keyword and you provide your different cases, they are chosen at random for which case gets picked. I cannot stress that even more, the fact that it is a random choosing pattern for what gets picked on the cases. So if you do have two cases that are satisfied and have items available on their channel, they'll get picked at random. But the default case will only get picked if none of the cases are met. That's still as expected for any programming language. So talking more about the fan-in pattern here, we have our worker. Our worker receives messages from two channels. The first channel holds numbers, and the second channel holds messages. Then we have a signal, and the signal is something that, in this kind of pattern, you will have to implement for a fan-in pattern. And the way the signal works is that when the worker has received inputs from these channels, that we need to signal that we have finished processing that data. All right. So let's look through here on the main function. If you can't see, I'm just going to talk through it. So what we do here, and the purpose of this function is to just create a sum of the numbers that are pushed on. So count the numbers that I give you to the single worker. So here I create two channels, one for numbers, one for messages, and we have the signal. So signal is from the sync package that comes in native Golang. It's not necessarily a third-party package. And we create something called a wait group. If anyone's worked with other concurrency, more like concurrency, or has done their computer science degree, a wait group works a lot like a mutex, but more that it's a counting mutex. So you say, I want to mutually exclusively lock my thread until I have seen a certain number of something. So I've been called a certain number of times. We'll show what that looks like as we go through later. And then we have a finish channel, which will mark when everything has been officially done. So first thing we do is we tell the signal that you need to be called 3 times before you can officially close your lock. That's my wife. So yeah, so running back. So for the signal, we tell it count to 3. If you're called 3 times on the signal, then continue forward. We create 3 workers who receive items from these different channels. These workers here are the producers in this example. And then we have a go function here for saying wait. So this go function here is going to be the one that actually blocks our program, or is a way for telling our main function to actually exit. And then here we create an infinite for loop where we have a select statement. In this select statement, we have the two cases, one for the numbers channel and one for the messages channel. If we receive something from the numbers channel, and just moving here on the right, on the other side, we can say that this is our numbers channel and this is our messages channel. So the workers here will push items into these channels. And as the consumer, our consumer is our main function here. The main function will be pulling in, the main function will be pulling in the items that come through these channels. The real thing I want to point out here with the fan-in pattern, just to jump to the end of it, is just the fact that there is a select statement here. It's randomly choosing between the cases. And if we receive a number in our number channel, then we're going to add it to our total. And then at the very end, once all the workers have pushed all of their items to these two channels, we're going to print out the sum at the very end. And the sum here is only triggered when we hit that finished channel, when we've actually received something in the finished channel. And the only time that finished actually receives an item, because we're using this thing called a sync wait group, is that in the sync wait group, when we say this wait call, this is a blocking call. And the blocking call will actually wait until this is called 3 times. Now, why 3 times? Because we said here signal.add3. This is a pattern from other just concurrency patterns in the past. Something that's more of like a numbered mutex. So the people at Golang who work on the language said, hey, we're going to have people using concurrency, but we need actually native concurrency patterns. And mutexes is basically a staple for any language that has to have concurrency. So the sync package comes native with Golang. You don't have to install anything extra. And when you use a fan-in pattern, this is very common to use a wait group in order to block everything out. So cool. Before I go further, because we do have some time, does anyone have any questions about this specifically? Good. So let's go to the next one. And this is the last one for our common patterns. And this is the greedy consumer pattern. So for the greedy consumer pattern, which is also known commonly as competing consumers, you are creating a consumer that's prioritizing their data sources. So in the example from before with the fan-in pattern, the fan-in pattern is listening to multiple channels for inputs. But let's say you don't want to look at all of those inputs evenly, and you want to prioritize reading from one channel over another channel. Then you can implement what's known as the greedy consumer pattern. This pattern can be applied with any of the 2 previous patterns for fan-in or fan-out, and is really just something that you only add when you have the right situation. And the right situation can come across as, let's say, you are running in production and you know that your application is going to get more of one type of data than another type of data. A good example of this in the sense of emails is that when you get emails, you're more likely to open your emails than you are to click something inside of the email. It's just a normal thing. You might want to get your emails away from being opened, and you want to just throw them away, but you're not interested in the content. So other helpful things knowing about the greedy consumer pattern is they're helpful for quickly consuming items by assigning prioritization. And they can also help if you do worker or consumer assignments. So you can have, let's say, let's take an example. You create an application where you have 2 data sources. And you create 2 workers. You tell worker A, I want you to read more from the first data source instead of the second data source. But then you tell the other worker, I want you to do the exact opposite. You would still satisfy the requirement of being in a greedy consumer situation, but you've assigned roles, right? And the purpose of assigning roles when you do a greedy consumer pattern is more evenly assigning availability for having workers consume those items. The downside of using the greedy consumer pattern is there is a chance that you would not be consuming enough of the right information. So this is really only a pattern that you may want to use when you know your data inputs and how common things are arriving for one versus the other, or however many there may be. So with the code on the right, we have a worker, and we implement the greedy consumer pattern quite easily by doing a nested select statement. This is valid. I ran the code. It doesn't look maddening. This is a really rough implementation of doing a greedy consumer pattern, but for the sake of explaining things, it's quite nice. So we create these two nested select statements. The first select statement says if I receive something from my high priority channel, work on it. If I do not, then go to the next select statement. And then in here, if I receive something from the low prio channel, do something. But if I don't, skip through, continue going, reach the end of my for loop, and continue infinitely forever. In the generate section, in this generate function, this is really just a nice function for generating queue items of any number. So here, if I have my channel and I say a count of 100, then it's just going to add 100 numbers from 0 to 100 to that channel. Down here, I create two channels, one of size 10 and one of size 5. The first one holds 10 items, the second one holds 5 items. I create my single worker. And then in the single worker, I use two go routines underneath. I want to run these at the same time. I don't want to run the first one and then the second one. The first one generates 20 items on the high priority channel, and the other one generates 20 items on the low priority channel. If I showed you the console log for what this looks like when you run it, you'll see that the very first thing that happens is that either the high prio or the low prio, one of those items gets picked up. That I can't fight with because then we're talking about picosecond fighting, and I'm not going to do that. That's just the efficiency of the language. But then, on the second call from the worker, when it goes the second time around the loop, he's going to pick up something from the high prio channel. That's either going to be the first or the second item, and then he's going to drain the whole thing. He's going to drain the entire high priority channel until there's nothing left. Then he goes to the low prio channel. So that's the greedy consumer pattern and how that would work out. So cool. If anyone has any questions about this, feel free to throw it onto the slide link, but we'll save time at the end for a Q&A as well. So, since pizza's not here yet, we're going to keep going with the talk. But the next thing I want to talk about here is anti-patterns. So we understand some nice patterns that you may want to use when you use concurrency in Golang, but we want to talk about what you shouldn't do and what you should avoid when you use concurrency. So for these today, we're going to talk about 3 of the most common problems you'll come across when you use concurrency in Golang. First one's going to be explicit cancellation using channels. This is something that not necessarily is avoidable. This is unavoidable. And it's just something that you might want to know. A nice little nugget of information. The second one is race conditions. This is something that anyone who has seen a race condition before will feel like it's a nightmare because you can't always detect them easily. And then the last one is deadlocks, which is probably the most common situation that you'll ever come across. So let's jump into it. So for explicit cancellation here, early cancellation is dangerous. If you're executing multiple go routines in a concurrent program, you may know when all of your go routines have finished, but you also may not. A good situation of that is saying that you run your application 24 hours a day, 7 days a week. And of those 7 days a week, you only really receive inputs at the beginning of the day, each day. And then for some unknown reason, your application dies in the middle of your high peak cycle. And you have a lot of inputs coming in. And that channel, when the main function has ended, that channel still had items in it. So you lose that data. That sucks. And can you recover it? You can't really recover it. So that's a cancellation, but an explicit cancellation here is when your main routine ends. And a lot of the functions before, or a lot of the examples before, I showed that at the end of my code, I did something. I created a while loop, or I created a blocking line of code to stop the main function from exiting. And if you didn't have that there, and you let your main function continue, then what ends up happening there is your main function ends because it's a Go routine. Everything in Golang is Go routines. If you have a single application with no Go keywords and no Go routines, you still got a Go routine. It's your main function. But when that one ends, all the Go routines that the main function had generated all get told, kill yourself. Stop executing. I don't care how far you are in your execution process, just go die. It's very negative. But that is explicit cancellation. So you have to be aware of that. You have to know those conditions, and you have to create your application such that it never does hit that situation if you still have items to work on. If anyone's interested, after this talk, I've worked exclusively with this for the last couple of months, and there is a nice way to do it where you can do what's known as a graceful termination of your program in Golang, and it's extremely easy to do. But in this example here, how do you fix that? How do you prevent that situation? You use the sync package. We used it earlier when we used wait groups. The sync package is native to Golang. I'll say that again, it's native to Golang. But you have to trust in what's also known as the defer keyword. So the defer keyword is a really easy way, and it's used here. But the defer keyword is a way of telling Golang, I want you to execute something, but I want you to execute it after you exit from my current scope. So in this example here, let's say this is a function that I've called. When I say defer, after I hit the end of my function and I've exited, then I will execute anything that has been deferred. And in this defer function, I have a blocking call to wait on something. Now, just for clarity, I have a function, I've exited from the function, I deferred something, but the defer statement is a blocking call. So when I exit the function, do I actually exit the function? You don't, because I have a blocking statement. So you will not actually finish executing this function until this block statement is closed and has continued on to hit the final finish line. So when I say trust in the defer keyword, I say use it to its highest extent of actually deferring these blocking lines of code to hold your application from continuing forward. In this example here, just for higher explanation, this is a situation in which you would have an explicit termination or an explicit cancellation. So we try to push 5 items to the queue, and then we print a line, but this is a non-blocking line of code, so it just continues forward. And those items in the queue never get processed. But in this situation, we actually do get to have the time to process everything in that queue. This is probably one of the first situations here we're using this thing called close, the close keyword. It might be a little hard to see because of the video or the quality, but it says close here. And so the question I had is, what does the close keyword do? What's the purpose of it? And what happens here is that when you use channels, whether they're buffered or unbuffered, you can actually explicitly close a channel, which basically means I don't want you to accept any more items into your queue. And then the next question came up, well, if you close a channel, can you still read from a channel? And the answer is yes. Yes, you can. In fact, it's a really good thing that you do. Because what happens here is that when you close the channel, because it's a buffered channel, it may still have items in it. So what you want to do is you want to clear it out. You want to take all those items and still read through and get those items done. So what you can do here is when we have this for loop that's ranging over a function, for anyone who's new to Golang, when you range over a channel or if you range over an array, it's like doing a for loop and say go through each item index by index. But in this one, when you range over a channel, you say pull one item at a time, anything that is in the queue. even if it's been closed and it still has items in the channel, this is still valid. You can still range over a closed channel. Common misconception of channels in Golang. So cool. Awesome. So the next thing that we'll talk about here, continuing on the topic of anti-patterns in Golang, is detecting race conditions. So I was talking with a few people during the break, and race conditions, there's a fun story about it. But I like to use the example from Futurama, if anyone's seen that one episode with Dr. Farnsworth, where he's at a race, and it's a quantum physics joke. But he's at the race, and there's two horses that are differently named quantum particles, and the two horses finish the race, and the announcer's like, and horse A has won, and he was betting on horse B, and when horse B, but then horse B, it's funny, it's just a measurement thing. I lost the whole thing completely. But it's just the idea, like, if you have two things happening at the same time, worker A or worker B, who's, assigning a value to a shared variable, and you do it too fast, you may have a situation where you're trying to read from something that's currently being written to, or you may get the wrong value. So what ends up happening there is it's what's known as a race condition. And the reality of this, I'm not stressing this enough, but I want to stress it now. When you have a race condition, these are nasty. And they're probably the nastiest problems you'll ever come across in concurrency as a whole, whether you do it in Golang or you do it in any other language. It's the nastiest of them all, because you'll never see it coming. And the reason for that is because race conditions have really hard concrete criteria that cause them to happen. This is one example that I'm going to explain here about when a race condition might happen. But there's so many other situations, and really it's just, in a nutshell, it's when you're trying to compete for doing the same thing in a non-thread safe situation. So this is an example, and we're going to go through it. But the way you fix it is by using something called the atomic package. So in this example here, this is the bad code, and this is the good code. So the bad code here is this main function. And in this main function, I have a shared variable called swap. It's a number. Holds 0 or it holds 1. That's it. I have two go routines that are executed at the same time, one after the other. The first one is going to set that swap variable to the value of 1. The second one is going to set the swap value to 0. Both of them run infinitely, since they have this for loop with no condition. At the very end, this is just something to say sleep for 5 milliseconds. And this is how fast a race condition can occur. These two functions run at the same time. I'm waiting only for 5 milliseconds. In that time span of 5 milliseconds, even 1 or 2 milliseconds, I've caused a race condition before it even happened. So I'm trying to do these assignments at the same time. And if you were to run this into code, it wouldn't throw an error. Flat out. If I said go run main.go, nothing would go wrong. Everything would be totally fine. Nothing would be bad about this code. This doesn't cause a compilation error. This doesn't cause a build error. No runtime error at all. But if I were to put something down here to inspect the value of swap, I would not get the same result every time. I'd get something different. So that, by definition, is a race condition. So how you fix that is basically you use something called the atomic package. And the atomic package is saying that if I'm trying to access something or assign a value to something that is in a non-thread safe situation, then do something to make it thread safe. So what we do here is we say atomic.store int64. I give the address in memory for where the swap variable exists, and then I assign the value. This would be a blocking command that runs in a separate Go routine to wait until this is not being written to. and I'm allowed to write a value without competing against another Go routine to assign the value. And by doing that, I won't run into a race condition. I didn't put a slide in here, but if you want to easily detect race conditions, just add the raced flag. So you would say go run -race main.go. And then in the compilation of your program, Golang will try to detect if a race condition can occur. And 9 times out of 10, it'll actually detect the race condition before you've even ran your program once. And that race flag is actually added to go get, go build. Almost all Go commands that are native with the Go command that's installed on your computer has the race condition. So very, very nice thing to know. So cool. So let's go to the next anti-pattern and our last anti-pattern, and this is deadlocks. So a deadlock situation occurs when you have multiple Go routines trying to do something, but then let's say you have a blocking line of code in one Go routine, and you say, I'll paint a situation here, and we have it here as shown. So I want to read something off the queue, but I have another Go routine that's trying to push an item to a queue. This is an unbuffered channel. Queues, channels, same thing, but this is an unbuffered channel, which means that when I try to push something onto my channel, I need someone available to also read from that channel. If you go online about reading about deadlocks, about like simple examples for Golang, you're never going to see something like this because this is something that I had put together. This is 5 lines of code to explain how easy it is to cause a deadlock. That's it. So what ends up happening here is as this Go routine is running separately in another thread, trying to push an item, this one is also trying to wait for, they're both trying to pull items off of a channel. My apologies. So because they're both trying to pull an item off the channel, and never does anyone push to the channel, they'll wait infinitely. And then that is a deadlock. Because they wait infinitely and then your program never exits. It's got no extra commands to run. Is there an easy way to detect this? Yeah, actually. And in fact, it's native to Golang, as always. But if you have a situation like this in your code and this occurs, then the error prompt will actually exit your code and it will dump out to the command line saying you've reached a deadlock scenario, fix your code. But it gets even better than that. It actually points to where in your code, the exact line and the exact column, and it would point right there for where the deadlock occurs. So how do you fix that? You do something like this. Make sure you prevent the deadlock scenarios by actually not causing them. So what we did here is that our situation was caused by trying to read twice from a queue. So what we do is we create another Go routine that pushes 2 items to the queue to satisfy the conditions. And then this will exit successfully. So cool. So to close out, I do hope that everyone kind of picked up a little bit of something about concurrency in Golang and how concurrency is native to Golang and you don't need additional packages unless you want to use the sync package or the defer keyword or the atomic package. Those come native with Golang, so you don't have to install them as extra. But I use concurrency on a daily basis for my applications and they're fantastic. The patterns that we explained today, they exist to help simplify concurrency and the understanding of it. Half the battle in concurrency is making it easy for your coworker to understand. So by using those patterns, you kind of start that process of adoption for your team. And anti-patterns, as we talked about today, is helping us understand what we should avoid. So those are 3 of your most common anti-patterns. There's more out there. I encourage everyone to go and find them and report them because there's far too many ways that you can have bad concurrent code. but there's also many ways that you can enjoy concurrency as a whole. So overall, I hope the message of my talk is have fun. Golang is meant to be fun. Enjoy it. Be concurrent. And remember the difference. Concurrency is everything we talked about today. Parallelism, something else. So thank you. And if we have any questions, we'll take them now. But thank you for hearing my talk.